In this section, we're going to be looking at linear transformations. That's what this chapter is on. And to start with, we just define what a linear transformation is and look at, well, how do we check to see if something is a linear transformation or not. So basically, a linear transformation is something that takes a vector in one vector space and transforms it into a vector in another vector space. And it could be that both of these vector spaces are the same. It just depends. But it's just a function that does some kind of transforming of a vector. They give an example right off the bat. The transformation of a vector equaling x negative y. And the way this works is, you can think of the left as function notation. This is our function called our transformation. This is our input, so we're inputting a vector that's in R2. And when we input it, our output is going to be the same x, but the opposite y. So for example, if we want to transform the point 1, 2, that becomes 1, negative 2. The same x with the opposite y. Now, this one, we can think about it visually. If we have 1, 2, and 1, negative 2, if we keep an x and just have the opposite y, that's just a reflection across the x-axis. All that is doing, it's transforming a vector or a point to something that's reflected across the x. We had the transformation negative x, y. This would be a transformation that reflects across the y-axis. You input the point 1, 2 this time, we get negative 1, 2. 1, 2 being right here, negative 1, 2 being right here. We have the same y value, but we have the opposite x. So that's just a reflection across the y-axis. And sometimes we can understand visually what's going on in a transformation, but not always. Especially when we get into transforming things from one vector space, for example, R2, to another vector space, R3. For example, we could have a transformation that the top coordinate adds the x's and the y's, the middle coordinate doubles the y's, and the bottom triples the x's. So if I want to transform the vector 2, 3, then my top coordinate is 2 plus 3. My middle one is 2 times 3. My bottom one is 3 times 2. So that's taking something in R2 and transforming it into something in R3. So it's just a function that takes a vector and then transforms it into another vector. But not all of these transformations are considered linear transformations. So how do we determine if they are indeed linear transformations or not? So in order for something to be a linear transformation, if we have two vectors u and v, let's say that they're in the vector space v, then if we transform u plus v, that must be equivalent to transforming u and transforming v and then adding them together. And that's not true for every function. So if it's not true, then it's not a linear transformation. It's some other type of transformation that we're not going to deal with. Another property is that if we have a scalar times a vector that we're transforming, we have to be able to pull that scalar out front and transform that vector, then multiply it by a scalar. Just a couple quick notes. In this book, they'll use these two notations interchangeably. We're more used to seeing functions written like this, where we have a parenthesis around our input, but sometimes they'll use that. We understand that T stands for transformation or transform, and this is the transform of V, which is what that means. So just be aware that these two mean the same thing. So in the book, they write it like this, but that means the same thing as that. So for the homework problems, we're going to be checking to see if things are linear transformations or not. But before we look at how to demonstrate that, let's look at one example of taking something that is in R2, transforming into something of R3, and see how this could make sense in a physical setting. Let's suppose we have two raw materials. I'll just make something up as I go. Let's say we have wood and we have screws. So these are our inputs. And then let's say we make three different things. We make tables, chairs, and wood floors. And those are our outputs. So this is an example of how we're comparing one thing that has two items in it, wood and screws, to something that has three items. Now, what we might actually do with this as a transformation is say, I want to produce items X, Y, and Z. What were those? Tables, chairs, and wood floors. How does that relate to how much wood and how many screws do I need? So I would have some way of relating these variables to wood and screws. So when I go to order those supplies, I'll be sure to order the right amount. So we don't, while our tendency is always to think of things spatially, thinking, well, when I'm transforming something, I've got something that's pointed in this direction, and then when I transform it, it's pointed in this direction. That's not always necessarily how we need to think about it. We need to think about what are we given and what are we trying to accomplish. So in this physical setting, we have these items we need to produce. What do we need to produce those? Not the same number of items in both categories, but it's a relationship between the two categories. So that's a transformation. So let's look at an example, and let's check to see if this particular example is a linear transformation or not. Let's suppose we have the transformation where we input xy and we output 1y. So we're transforming from R2 to R2. So we need to check to see if our two properties hold. So let's let vector u be x1, y1, and vector v be x2, y2. And remember, we need to check those two properties, that the transformation of u plus v has to equal the transformation of u plus the transformation of v, and alpha times the transformation of u or v has to equal the transformation of alpha times u. Now, I'll tell you what, to make this simpler, let's go back and change these. Instead of x1, y1, let's call these u1, u2, v1, and v2. So if we transform u, we put the u1 coordinate in, we get a 1. We put the u2 coordinate in, we get u2. We transform v, we get 1 and v2. So the transformation of u plus the transformation of v is 1 u2 plus 1 v2, which is 2 u2 plus v2. So that's doing that side. Now let's see what we get when we add u plus v and then transform our result. So we want the transform of whatever we get when we do u plus v. Well, u plus v, if we add these together, it's u1 plus v1 over u2 plus v2. So that's adding those two vectors. When we transform that, our transform says that our top value is 1, the bottom one is whatever that is. Now notice, those are not the same. When we did the transform of u plus the transform of v, we got this. When we did the transform of do u plus v first and then transform it, we got that, which noticeably the top coordinate of those vectors, the top elements, are not the same. So since those don't match, this is not a linear transformation. All right, let's look at another one. Let's look at the transformation of x, y, z. So we're taking something in R3 and we're transforming that to 0y. So something in R2. So again, let's let u be u1, u2, v, let's call that v1 and v2. So u plus v, u1 plus v1, u2 plus v2. So when we transform u plus v, our top coordinate is 0. Our bottom coordinate is whatever. And you know what? I botched this. This is the only thing about making these videos, that Now y'all see where I made a mistake. Where our input has 3 values. So our U is U1, U2, U3. Our V is V1, V2, V3. So we need another row here. U3 plus V3. Okay. So when we transform this, our top value is 0. Our bottom value is whatever y is, which y is that middle one. Our middle one is U2 plus V2. So that's what we get from the transform of U plus V. Now let's do the transform of U plus the transform of V. The transform of U, remember U is this. So it's 0 for the top one, Y, which is the middle one, for the bottom. Then the transform of V, 0 for the top, Y for the bottom. So when we add them together, we get 0 on top, U2 plus V2 on bottom, which notice that's the same thing we had there. So that the first property matches, now we need to show that alpha times a transform of V equals a transform of alpha times V. So if we do the transform of V, the transformation of V, 0 on top, the middle value on bottom, and that gets multiplied times alpha. So if we do each of those times alpha, we get 0, then alpha V2. Now if we do the right side, alpha times V, that's alpha V1, alpha V2, alpha V3, because remember V is in R3, V1, V2, V3. So alpha times that, alpha times each of those. So when we apply our transformation, it transforms into R2, where our top value is 0, our bottom value is that middle one, alpha V2. And notice that works. So since both of our properties work, since the transformation of the sum of vectors is equal to the sum of the transformations, and since a scalar times our transformation equals the transformation of a scalar times our vector, since both of those are true, this is a linear transformation. So that's what we're going to be doing on these. We're going to be taking 2 generic vectors in whatever space our input is, and we're going to be checking our 2 properties. Does that equal that? And does that equal that? So if those properties hold for the transformation, then yes, it's linear.